good? So I'd like to thank the organizers for inviting me to this Stimulate conference. I apologize for the fact that my lecture topic is not directly related to anything that Wolfgang worked on. However, if you kind of look into the foundations of Ricci flow, you certainly see that that the geometry of non-negative curvature plays a very important role, and Wolfgang made fundamental contributions there. Okay, so I'm going to be talking about Ricci flow through singularities. This, of course, if you look at the title, you can see has some overlap with what Valentino Tassati was talking about before. However, the overlap turns out to be rather limited because the context is different, and so the techniques and the main kind of objectives, at least at the moment, look rather different. But I'll come to that later. So, right, so the setup, yeah, so this is joint. This is about joint work with John Lott. Right, so Hamilton proved short time existence and uniqueness for the Ricci flow equation. Right, meaning if you have a compact manifold with a smooth Riemannian metric, right, so then you can solve the Ricci flow equation on some maximal time interval. Okay, so you have some canonical evolution of your initial smooth metric, and that's defined in this maximal time interval up to time capital T. So if capital T is finite, so you can't extend the flow past that time, then Hamilton showed that what's going wrong is that the curvature is blowing up. Meaning it's not, the curvature tensor does not remain uniformly bounded on the time interval up to capital T. Okay, so this is the blow up time. So the simplest example, instance of this is when you take a round metric on the n sphere. So D0 is the standard metric of time T1. In that case, the metric of time T is just the original metric multiplied by this affine function of time. And so of course the radius goes to 0 as time goes to 1 over 2 times n minus 1, and the curvature blows up. Right, so that illustrates the blow up phenomenon. There we go. It keeps cutting in and out, right? But let me try moving a little higher circle threshold. Okay, so another metric, another example to think about is what people call the barbell metric. So for this, you take two round metrics on the 3 sphere, and then you glue them together by a neck region. So in this region here, that was not good. In this region here, you have neck-like geometry, so up to scaling, let's say the metric here looks like a round metric on the 2-sphere product with R, okay? And where the 2-sphere has small diameter. So in that case, right, the Ricci curvature here is very, very large, positive. And so because of the minus sign there, right, this will tend to shrink rapidly. And as it shrinks, the curvature gets bigger, so it accelerates. And so heuristically, what you expect is that after a short amount of time, again, this is just, of course, a schematic diagram here, since we're talking about a Riemannian metric, but after a short amount of time, kind of the radius here will go down to 0. And again, heuristically speaking, it's plausible that during that time interval, the curvature out here was initially small, or not big, and it didn't have much time to grow. Okay? Of course, justifying that heuristic is actually pretty non-trivial. But it turns out to be true, and so what ends up happening is that this thing, again, blows up in finite time, but the metric is only blowing up on a certain closed subset of the manifold. Okay? So elsewhere, so out here, you have an open set of points where the metric actually has a smooth limit as you approach the time capital T. Okay? So this is very different from the situation here, because at the singular time, in some sense, a big part of the manifold is still left. Okay? Even though there's some blowout that's occurred. So this leads to the question, can you continue to flow past the first singular time? Okay, versus this came up in Valentino's talk. And of course it occurred to Hamilton when he first started thinking about the Ricci flow in the 70s and 80s. And so one way of answering that question is to use surgery. Okay, so because this is important in the rest of my talk, let me say a little bit about this. Okay, so the idea of surgery, Ricci flow surgery, to remind you, is the following. So let's think about this neck pinch example that I was just talking about, right? So, so what you can do is to run the Ricci flow either all the way up to the first singular time, or perhaps slightly before the singular time when the curvature is large but hasn't yet blown up. Okay, but so let's say we run it up to the singular time. So then we have this smooth limit, which is defined smooth limit on an open subzone. And so the idea is, now we can't continue the Ricci flow because it's on a non-compact manifold. What we do is we look for a place in the manifold where the curvature is large. And we look for a neck-like region there, and we look for, in the neck region, we look for cross-sectional two-spheres, and we cut the manifold along the cross-sectional two-spheres, okay? And then we throw away the part of the manifold where the curvature blew up, and also the part where it had a limit, but it sort of lies on the wrong side of those cuts, okay? So we want to throw away a part of the manifold. Now we have a manifold with two-sphere boundary components. And then we glue on caps with appropriate metrics, so these glue metrics with nearly non-negative curvature. Okay? So now we have a compact Riemannian manifold again, compact smooth Riemannian manifold, we restart the Ricci flow. Okay, so Ricci flow in surgery is the process which alternates between Ricci flow and then the surgery process, which I just described. Okay? So that's the notion that goes back to Hamilton, and so this was used successfully in two cases. So one is in 4D, when you're looking at Ricci flow under this curvature assumption, positive isotropic curvature. And then in 3D, this was done, initiated by Hamilton, and it was completed by Perelman for general 3D metrics. Okay? And this was, of course, hugely successful. Right? So it gave a proof of Thurston's geometrization conjecture, particularly the three-dimensional Poincare conjecture, and it gives a classification of four manifolds with positive isotropic curvature. So that's great. However, you might notice that if you look at this process of Ricci flow in surgery, you can see it's not a canonical process, right? When we're at the surgery time, I have to make choices where it chooses the two spheres, how I move the caps on, and so on, right? So it's not canonical. And so it leads you naturally to this question. So Perelman, who was the first to successfully construct the flow in surgery, asked this question. Right? So it's likely that by passing to limit this construction, one would get a canonically defined Ricci flow for singularities, but at the moment I don't have a proof of that. So what he means here is imagine taking a fixed compact Riemannian three-manifold as your initial condition, right? And then you run the Ricci flow in surgery, okay? And then you start over again where you run the flow in surgery, but the surgery parameters, like the scale at which you do the cutting, you make smaller, okay? So you run it again and again. So you take a sequence of these Ricci flows with surgery where the surgery is taking place at a finer and finer scale. Intuitively, this is happening closer and closer to the singularity, and intuitively you think that somehow, because the scale is going to zero, it won't affect the flow. The effect on the flow will be smaller and smaller, and you'll get some sort of canonical limit object. Okay, so that's what he's asserting here, and he also says so our approach is aimed at eventually constructing a canonical Ricci flow to define the largest possible subset of space-time, a goal that has not been achieved yet in the present work. So I actually find it rather amusing. This is on, I think, the first page of his second Ricci flow preprint. I mean, this is a preprint that solves the geometrization conjecture, but you pretty much have to read the introduction through 3 times before you realize that he's actually claiming to solve this. And instead, like in the first page, he's talking about how he has not really succeeded in reaching the goal that he wanted to get to. Anyway, so these are really this is one motivation for the project that I'm going to talk about. So more explicitly, how can you formalize Perelman's assertion here? He has not defined, so you say passing to the limit, what notion of convergence you're using. If you're talking about a Ricci flow through singularities, well, what is that? Okay, so and so on. Okay. All right. So if you stand back and you think about this, then you realize that it's part of kind of a more general, fairly generic discussion in PDE, or more specifically in geometric PDE, right? In all these instances of we're looking at geometric PDEs. For each of them, there's a very old notion of classical solution, but there are natural contexts where you do not expect to have a classical solution, so you have to define what the weak solution is, or what generalized solution is, and then once you've done that, then you can begin to discuss the structure of these solutions. Okay, so in particular, you want to prove existence of weak generalized solutions. When it's relevant, you want to prove uniqueness, and so on. Partial regularity. So that's another perspective on this. The case that's closest to the one that I'm going to be focusing on is really mean curvature flow. So of course Toby discussed this. And the case which is closest to Ricci flow, I think, is where you're looking at surfaces flowing in R3, where the surfaces are assumed to have positive mean curvature, okay, the mean convex. So in that case, the structure of singularities and flow of surgery and so on looks very similar to what one has for Ricci flow in dimension 3. And a long time ago, in the case of mean curvature flow, notions of weak solutions were developed. I mean, for example, Ricci in the 70s defined Ricci flows, which are defined using variables and ideas from geometric metric theory. Then there was the level set flow, which Toby talked about. So there you can evolve an arbitrary compact set, for example, under mean curvature, using this notion of a viscosity solution. And then there's also the notion of mean curvature flow at surgery, which is very similar in spirit to what I described before for in the case of Ricci flow surgery. Okay. So if you look, again, in this case of mean curvature flow with positive mean curvature, this work of White and Sinistrari that really tells you, gives a beautiful picture, and it shows that in this case, the notions all agree. Okay, so in the natural sense, the level set flow matches the Ricci flow. So you have kind of a unique weak solution. And also, the analog of Perelman's assertion, right? So Perelman's assertion was that if you take a fixed initial condition, and then you run a sequence that flows with surgery, where the surgery parameters go to 0, then that actually does converge to the other notions of weak solution. Okay. So when you compare that with the Ricci flow case, the big difference is you don't have a notion of, you don't even know what the notion of the weak solution should be, or what the notion of convergence is. Okay, but this is the big inspiration for what we're doing. In particular, in the Ricci flow case, if you start contemplating trying to do something analogous to what works in curvature, then you find yourself looking at trying to make sense of Ricci curvature for very singular objects, right? which leads to huge technical obstacles. Okay. So before I kind of get to the main thread, let me just mention some related work. So people have looked at the case where you have, in Ricci flow, you have an isolated singularity occurring, and then you flow out of the isolated singularity. So this was done Feldman, and Knopf. And then there's a papers by Knopf, Knopf, where they do this, and they also, so they flow into a generic net pinch, so they study very closely the kind of singularity that I was talking about earlier, and both the before and after pictures, and match them up with good control over the asymptotics. And then there's a large literature on Kleiner-Ricci flow through singularities, which of course Valentino was talking about. So I just mentioned some of the names there, and maybe this is a somewhat random choice. I could put many more names there, but I was trying to focus on the papers which looked at both before and after, right, as opposed to one or the other. But I would just mention, and Valentino also did this, mentioned this in his talk, that there's some sort of key rigidity properties or special features of Kleiner-Ricci flow, which are completely absent in the real case. So one of them is the fact that Kleiner-Ricci flow is a scalar equation, and so you can talk about viscosity solutions or use other techniques, the comparison techniques, which are only valid for scalar equations. And then, for example, there's the fact that you know exactly how the Kleiner class evolves under Kleiner-Ricci flow, and this allows you to say exactly when singularities will occur. And as Valentino mentioned, the singularities occur in a very, very special way, and they're closed sets with a very special structure. And so none of that is true you could wonder if some weak form of that might be true in the real case, but it's very far from being known at this point. Okay, so that's kind of background and motivation. So let me kind of move toward the first theorem. So to do that, I need to talk a little bit more about Ricci flow with surgery. And this is going to be, in places, this is going to be a very rough description just because of the technical nature of the precise story. Okay, so the first thing I need is a kind of a crude notion of Ricci flow with surgery, and that's just the notion of a basic concatenation of classical Ricci flows with surgery. You run the flow until it goes singular, you look at the set where it has a smooth limit, you throw something away, move something on, and restart. Okay? So you can formalize that as follows. So we have a sequence of Ricci flows, so they're defined on manifolds which are themselves changing, right, because the topology can change. Time intervals, which where the initial time and the final time of one flow matches the initial time of the next. And I'll assume that the flow GK goes singular at the right endpoint. Okay? So there'll be an open subset of the manifold MK where the metric has a smooth limit, so-called GK bar, as you approach the right endpoint. And then we'll have inside this smooth limit, inside this open set omega k, where the metric has a smooth limit, you select some subset which you want to keep. Okay, and then you throw the rest away. The part you keep is going to be a compact manifold with boundary. Okay, and that's what I call xk plus, right? And then I want to formalize what I mean for adding something to that to get a compact manifold, which will be the initial condition for the next flow. So to do that, I'll just think of taking this part which survives the surgery, and then I take an isometric embedding, say CK, of that into the initial manifold, compact harmonic manifold, MK plus 1. Okay? So therefore, it's the difference between the whole manifold MK plus 1 and this image, which is what you're adding on. Okay? So that's the setup. And So Perelman constructs such a Ricci flow starting from any initial condition in the 3D case, but it satisfies much stronger conditions. So I'll just describe these very informally. So first of all, Perelman's Ricci flow surgery is done with control along the control of the surgery. So the cutting you do along necks, or cross-sectional two spheres in necks, where the necks have a certain scale and a certain quality of approximation to the round neck. And then what you glue on is a surgery cap, which again is agrees with some model up to some error. And then there's a pointwise curvature condition, which holds globally in the flow, which is the Hamilton-Ivey pinching condition. I'm not going to write this down, but I just want to mention two consequences. One is that this pointwise curvature condition implies that you can control the full curvature tensor just knowing the scalar curvature. Okay? And it also implies that when the scalar curvature is large, the curvature looks almost non-negative, right? In the sense that the lower bound of the sectional curvature is like the bound of the scalar curvature, then you divided by the log r. Okay? So this is what implies that in the story of 3D Ricci flow, singularities are positively curved. And then finally, there's what Perelman calls the canonical neighborhood condition. And informally it says if you pick some point and the scalar curvature at that point is large, bigger than some threshold, well then the whole flow near that point on the scale comparable to the curvature looks close to a model flow. Okay? And there are two possibilities for the model. One possibility is what's called a kappa solution. So a kappa solution is a 3D flow that's ancient and has bounded curvature and has non-negative curvature. Okay? It has some other conditions as well, but essentially you should think of this as the standard example of a kappa solution is just a shrinking round cylinder. Okay? Another example is the Bryant soliton, or you can think about a shrinking spherical space form. And then the other case would be where you have a point, the point which happened where in the recent past a surgery has occurred. Okay, in which case the model will be the standard post-surgery model solution. Okay. All right. So these are the conditions that these guys satisfy. And now I want to shift to a space-time picture. So the Ricci flow space-time. So this is a tuple. So you have a four-manifold, a smooth manifold with boundary. Okay. It has a time function on it. So this is a submersion to the non-negative reals. The boundary of this manifold, the boundary is precisely the level set, the zero level set of the time function. Okay. And then this thing I'm calling d by dt, that's going to be a time vector field. This is just a vector field with the property that the integral, if you move along the integral curves, the time function increases at unit speed. And then, so this is the space-time picture, so we need to have the flow. So the flow corresponds to an evolving metric on the time slices, right? So if you look at the spatial subbundle or the tangent bundle, which is really the kernel of the differential of time, so you have these time slices, so you have Riemannian metric building on those, and those should satisfy the Ricci flow equation in sort of the natural sense. So the lead derivative of this metric with respect to the time vector field is minus twice Ricci. Okay? So if you look at this structure, so it's a smooth manifold, okay? Smooth four manifold. You pick any point and you look at a neighborhood on a small scale, it just looks like essentially like an ordinary Ricci flow in the sense that you take a time cross section and then you flow the metric forward and back. If you use a flow chart, it just looks like locally like a Ricci, smooth Ricci flow. Okay. And now, some notation for the A time slice and then time slab. So if you have a Ricci flow with surgery in the sense of Perelman, well then you get a space-time from that, basically, right, you have this flow with surgery that I was talking about before, so you get a bunch of time slabs, so you just glue them together, okay, essentially using the diffeomorphism that showed up in the definition. Okay, so I'll just think of this space-time as being like the Ricci flow of surgery. Okay. So now I can state the theorem. So if you have a sequence of 3D Ricci flows with surgery, in the sense of Perelman, where the initial conditions, I'll assume, are isometric to some fixed compact Riemannian three-manifold. And if you look at the jth Ricci flow with surgery, then delta J, which is a parameter that shows up in Perelman's discussion, that as value times 0 should go to 0 as J goes to infinity. Okay, I don't want to say what this delta J is, but because it plays several different roles in Perelman's construction, but one of the roles is that, I mean, if delta J goes to 0, well then the scale at which the surgeries are being performed goes to 0. Okay? And the quality of the next goes to, gets arbitrarily good and small. So under these assumptions, then after passing to a subsequence, the sequence of Ricci flow spacetimes will converge to some limiting Ricci flow spacetime. Okay? In a sense that I'll describe below. So what is so standing back, what this is saying is that, I'm sorry, I'll come back to that in a second. Right, so what this is going to say is that we have a sequence of Ricci flows spacetimes MJ, and there are kind of bigger and bigger sets in the MJs, which look closer and closer to bigger and bigger sets in the limit. Okay, that's the notion of convergence, which I'll spell out in a second. But when you think about this theorem, just think about the neck pinch case that I was talking about before, right? So you have a sequence of Ricci flows of surgery, where you do the surgeries at finer and finer scales, and I'm saying that there's some limit object there, which is this limiting Ricci flow spacetime. Okay, but in this setup here, there's no statement that we're looking at a generic neck pinch, and in principle, you could have sort of in the limit, you could see maybe kind of infinitely many neck pinches occurring, accumulating on this first singular time. Okay, so more precisely, so this is the notion of convergence. Right, so we get a sequence of diffeos here, Vj, it's comparison diffeomorphisms, taking an open set Uj and Mj to an open set Vj and M infinity. And the idea here, so to make sense of the assertion that these are defined in larger and larger sets, you just realize that there are two kind of natural exhaustion functions living on the Ricci flow spacetime. One is the time function, right? And the other is the scalar curvature function. So the idea is that if you fix an upper bound on time and an upper bound on scalar curvature, right, this gives you a subset of space-time, and then you let both these parameters into infinity, that gives you an exhaustion. And the assertion is that if you give yourself an upper bound on time and a scalar curvature, then for large J, the Uj will contain the corresponding set in Mj, and Vj will contain the set in M infinity. Okay. And this map, in addition, it preserves the time functions. And asymptotically, so if you look at asymptotically preserves the Ricci flow, so and time vector field. So if you push forward the time vector field on Mj and the metric tensor on Mj, then those converge smoothly on compact sets to the corresponding objects in M infinity. Okay. So this limiting Ricci flow spacetime inherits some nice properties from the approximators. So in particular, in the Ricci flow with surgery, there's a uniform lower bound on the scalar curvature, and that passes the limit. It's a little bit less obvious, but it's not hard to see that the scalar curvature actually is a proper function if you bound time from above. So if you look at the part of space-time where time is bounded by capital T, here T is some number, it's not a blow-up time. Well then, the scalar curvature is proper there.
So is it set up in such a way that your time function itself is proper? I mean, are there actually space-time points included where the surgery occurs, or
no, the function is not proper by itself. In fact, that's a good thing to think about. So in this example here, if you look at the singular time, so what you'll see is, I mean, the singular time slice will be something that's non-compact, right? And it has two ends corresponding to going out this neck region here and that neck region there. Okay? So the thing is not proper even when it's restricted to a time slice. I mean, the time, yeah.
And yet
Well,
you're saying
that's the. Yeah.
But that doesn't mess up the properties of the scalar curvature?
What I said a second ago, I was actually incorrect. If you stick the time function to a time slice, it's like it's a constant, right?
Right, that's why I was worried.
So the scalar curvature is proper because what's in this example, and the idea is as you go out this end, in fact, the scalar curvature flows out. Okay? So if you fix your attention to this time slice, the set of points where scalar curvature is less than some threshold stays away from the singularities. Okay? And what's being asserted here is a similar statement, but in space-time. And now this also satisfies, it satisfies the Hamiltonian pinching condition and then a canonical neighborhood assumption. These just routinely pass. You just pass these conditions to the limit because they're essentially point-wise conditions. Okay, so they're inherited by the limit. In fact, the M infinity has to satisfy the stronger version of the canonical neighborhood assumption because if you look at a point with large scalar curvature in the limit, right, then the approximators, those points will be modeled either in kappa solutions or post-surgery solutions, but in the sequence, the surgery scale is going to 0. Okay, so those just sort of disappear from view. And points with large scalar curvature is modeled on kappa solutions. Okay, so this theorem gives a partial answer to Perelman's question, and it provides formalizes the notion of limit and convergence. Okay, and the subsequential convergence statement here. Okay, so motivated by this theorem, we'll make this definition. So a Ricci flow spacetime is a singular Ricci flow. It's four-dimensional. The initial condition is compact, and the conclusions of the theorem hold. Okay. So the previous theorem. So the scalar curvature function is supposed to be bounded below. The scalar curvature is proper. It should be bound time from above. Should satisfy the Hamiltonian pinching condition, and it should satisfy the canonical neighborhood assumption. Okay. So just a remark here. In fact, it turns out that you only need to assume the last two conditions outside a compact set. Okay? And then if you do that, then they hold globally. So the reason I'm making this remark is that that really means that taken together, these conditions are really asymptotic conditions on the space-time. Okay, so what this definition is, it's saying, okay, we want a notion of a generalized solution to the Ricci flow equation. Okay, one approach to that would be to try to look at some very singular notion of a Riemannian manifold and try to make sense of the Ricci curvature there. Instead, we're just taking that completely out of the picture. So we just look only at smooth Ricci flows. Of course, you can't just do that. You have to do something to replace that. And the idea is to then put in these asymptotic conditions, or like the boundary conditions at infinity, more or less speaking. Okay? So it's a very different approach than what's been used in other geometric flows. Or as far as we know, no one has ever done this in geometric PE before. So this is our notion of generalized Ricci flow. And so one consequence of this definition essentially is the following corollary. If you have any compact Riemannian 3 manifold, well then there is a singular Ricci flow that has that as initial condition. So you can solve the Ricci flow with any initial condition in this sense. And this follows just directly from the convergence theorem that I had before, because you simply take this manifold as your initial condition, you run Ricci flow with surgery, sequence of Ricci flow with surgery, the parameters go to 0, and apply the convergence result, and that will give you your singular Ricci flow. Okay. So, kind of circling back to, so with this definition, it's kind of a natural conjecture that you might make. So if you have two of these guys with the same initial condition, then actually they should do the same. So it's uniqueness, right? Same up to the obvious notion of equivalence. Okay. So this uniqueness conjecture, together with the convergence theorem above, implies affirmative answer to Perelman's question. Right? This is kind of a standard argument. If you imagine Perelman's conjecture were false, right, that would say that you had for a fixed initial condition, you had a sequence of Ricci flows with surgery, and you do not converge. Okay, so you could apply the theorem that I had before to see that you'd have to be able to pick two different subsequences and extract two different limits, right? And that would contradict the uniqueness. Okay, so this implies affirmative answer to Perelman's question. So I've been working on this with Richard Bendler, and I believe we have a proof of this conjecture now, but we have not finished. We have not finished writing it, so I'm not going to state anything now. Another remark about this uniqueness conjecture is, right, there are some situations where you might want to apply Ricci flow not to just a single Riemannian metric, but to a whole family, a continuous family of Riemannian metrics. And if that's going to be of any use, then you pretty much need to know that there's a unique solution. Okay, so that's another motivation for looking at this uniqueness. Okay. So let me say a little bit about the proof of the convergence theorem. So the first ingredient is kind of trivial, which is just this. If you start with a Ricci flow spacetime, you can promote that. So that in the Ricci flow spacetime, you just have a Riemannian metric on the time slices, right? So that's the time function. But you also have a time vector field, which is everywhere transverse to that. So if you combine these two ingredients, there's an obvious Riemannian metric that you can put on the spacetime that makes the time vector field unit vector perpendicular to the time slices. So then the spacetime becomes the Riemannian manifold in its own right. But let me mention, right, if you just think about this example here, you see that Riemannian manifold is incomplete. Even the time slices are incomplete. Okay? So this is kind of, technically it's different from what one is used to thinking about in Riemannian geometry. Okay, so then the next ingredient is a property of these space-time metrics. So it turns out that the canonical neighborhood assumption for the Ricci flows with surgery implies that the space-time metric doesn't imply it has bounded geometry, but it has kind of locally bounded geometry. Okay? More precisely, if you look, so it says the geometry of this space-time with the space-time metric, this is controlled locally as a function of the scalar curvature. Okay, so if you pick a point in space-time and you know the value of the scalar curvature there, you have an upper bound for it, well then there will be a ball whose radius has a definite size, depending on the bound scalar curvature, where you have curvature bounds. Okay, which again depend on the scalar curvature, and bounds on the injectivity radius, which depend on the scalar curvature, and also bounds on derivatives of curvature. Okay, so then there's a general compactness theorem for Ricci flow spacetimes with this kind of a local control of the geometry. Okay, it's some kind of cousin of elementary compactness theorem from Riemannian geometry, right? If you have a sequence of Riemannian manifolds, say with base points, right, and you know for every radius r, right, the curvature and its derivatives are bounded uniformly on R balls centered at the base point, right? And then you have a uniform lower bound injectivity radius at the base point. Well, then the subsequence of those Riemannian manifolds will converge smoothly to some smooth limit. So it's some sort of distant cousin statement like that. And so one can then try to apply this to the setting of these Ricci flow spacetimes. And there's another kind of key point that goes into this. I just want to maybe just ignore it. Just what would you have? One thing you have to worry about in a situation where you have pointed convergence is loss of mass, right? So if kind of the simple example of this that you see in geometry would be if you have a sequence of hyperbolic metrics on a genus 2 surface, right? I can almost take this thing back here. Right, you have a sequence of metrics where you have, say, a closed in the sequence. This homotopy class is realized by a closed geodesics whose length goes to right. In that case, the distance between these two punctured tori, if you like, tends to infinity. So if you choose a base point here and pass to a pointed limit, kind of half of the surface disappears from view, right? And so one could potentially have a similar thing happening over here, and you have to rule this out. So it's another ingredient in the discussion. Okay, so I hope that gives some idea what goes into the proof. In spirit, it's some sort of generalization of known smooth compact results. Okay, so now I want to say a bit more about these singular Ricci flows. So if you have a Ricci flow spacetime and a path in there is time preserving, so it's a map from some interval in R to the spacetime. Time preserving just means that if you take a point in the interval, the point real number t gets mapped to a point in the spacetime with time value t. Okay? So particularly these curves are kind of moving monotonically through the spacetime. So let's fix a singular Ricci flow. Maybe for most of the statements here are equally interesting in the case that the singular Ricci flow arises in the limit, but they're statements that hold whether or not the singular Ricci flow comes as a limit. So let's start looking at the behavior of the volume. So for every t, if you look at the time t slice, this has finite volume. This is easy to see for limits, but it's true in general. And right, if you look at the volume of the time t slice, then locally this is a Holder continuous function. And the upper right derivative is locally bounded. Okay, so this is not clear even for limits. Okay, so this is really kind of a new estimate for volume and for in the case of closed surgery. And then if you look at the sequence of volume functions that you get in the approximators, then those converge uniformly to the volume function in the limit. And the scalar curvature on any singular Ricci flow is integrable if you bound on the part of space-time with time bounded above. And then also you have the usual formula for the change in volume. Right? So if you have a classical Ricci flow on a compact manifold, then the fact that the scalar curvature represents the kind of from the Ricci flow, tracing the Ricci flow equation, you get the logarithmic derivative of the volume element is given by essentially the scalar curvature. You integrate that, what you find is that the change in volume comes from integrating the scalar curvature over the corresponding time slab, right? So this is a one-line calculation if you're doing Ricci flow on a compact manifold. In this case, it's actually quite non-trivial. The reason is that it has to do with the fact that the space-time is non-compact and it's incomplete, and the integral curves of the time function are incomplete as integral curves of the vector field. Okay, so this is It takes quite a bit of work and involves some sort of justification of integration by parts. And then also, if you look at the scalar curvature function, for every a less than 1, the integral of the 8th power of r is bounded on time slices. Okay, so that's the discussion of the behavior of volume. So there's some other properties. So I want to, maybe I'll kind of just skim over this. So in Perelman's work on Ricci flow and surgery, so a key part of the story is that you get a very good description of the part of the manifold which has large curvature, both locally and globally. And that carries over essentially by, I mean, you can use very similar arguments in this context. So maybe I'll just skim over this. I want to talk about something that is kind of an interesting feature that you can't really see at all if you just think about flow and surgery. So if you have in Ricci flow spacetime, if you pick a point x, well then you have the time vector field, right? So you can follow the integral curve, that time vector field, forward and backward in time. Okay? So the maximal integral curve, I make it parameterize it so it's time preserving. That's I'll call it the world line of the point x. And right, so in the example of this simple neck pinch, right? So if you imagine looking at this place where the curvature is biggest, right, and this thing pinches off, well, if you pick a point here on this two-sphere where the curvature blows up, its world line going forward will be incomplete. You can't extend it past the singular time, right? So, so this is kind of a generic phenomenon that the integral curves of the time vector field are forward incomplete. Okay, but I'll say a world line is bad if it's backward incomplete, meaning that that you can't follow it backward in time all the way to the time zero slice. Okay, so so we have a theorem which says that if you have a singular Ricci flow and you pick for some time t a connected component c of a time t slice, well, inside that connected component there are only finitely many points with bad world lines. Okay, so let me kind of illustrate this with a picture. So think about, again, the same basic picture where you have a neck pinch. But let's go past the singular time, right? So the neck pinches off, and then you go past the singular time. So at the singular time, you have some non-compact manifold. Again, what I'm saying is heuristic. One can justify this. In fact, it's discussed relatively explicitly in papers by Angen and Knopf that I alluded to. Right? If you go forward from the singular time, now you'll have two connected components, and then you have, again, schematically, you have kind of two fingertips here, right, which are rapidly receding from the singularity. Okay? And so what's happening here is that inside these fingertips, so in each fingertip, there will be exactly one point which has a property as you run that backward in time now, backward in time toward the singular time, it goes singular. Okay? And all other points in there, so in fact, near this, if you look at that fingertip, all the other points will safely pass through that singular time, and they can survive a definite amount of time. Okay? Maybe there'll be some earlier surgeries or something like that in the general case, but that's...
Sorry, why is that unique? That point unique? Could be right, kind of rotationally symmetric again.
If it's rotation is symmetric, then it's relatively easy to locate. So let me try to say a little bit about that in just 1 second. So particularly from this, there are only countably many bad world lines. So to the example that I was just discussing, right? There's this generic neck singularity. There are only, in this case, there are only two bad world lines coming out of that singularity. And the main part of the proof, and to prove this, we actually prove much more. We really validate this heuristic picture. that I was just describing to you. So in other words, we show that if you have a point with a bad world line, and you follow that up to the singular time, then really what's happening, it must be a point lying in kind of a fingertip region, okay? And moreover, there's only one point in that fingertip region which goes singular, and the others sort of survive, okay? Why is it unique? Well, there are two ingredients. So one is that if you have a point where, so imagine following this fingertip where until it's become nearly singular, okay? So then, from what's known about the structure of kappa solutions, so you should think of this fingertip region as being sort of very, very long, like this. So the scalar curvature is sort of controlled here, but gets bigger and bigger. Right? This distance is generically bounded. It stays uniformly bounded. So the curvature is blowing up, and then you'll have some region which has controlled diameter compared to the radius of curvature, where the metric does not look neck-like. Okay, so over here at each point, you look at it on the scalar curvature, it looks very close to a round two-sphere across R up mod-scaling. Okay, and there's a kind of a small region. Actually, on the scale compared to the scale of its own curvature, it has controlled diameter, and those are the points where it does not look neck-like. And so what one shows, so a key ingredient here is the stability result for necks. If you stay outside this zone at the tip, okay, if you pick a point outside this fingertip region, well then we show that so it looks nearly neck-like, and we prove a new stability result that says if you look sufficiently neck-like, and as you go backward in time, you continue to look neck-like. So it's very loosely speaking, it's similar to the result that Toby was talking about the stability result for cylinders. And so that tells you that at least the points which stay outside this zone are safe. They're not going to go singular. Okay? But then the diameter of this region, as you go singular, the diameter of this region gets smaller and smaller, and so you basically just use the contraction of distance going forward in time, and you get that it's a single point. Okay. So this fat property of the bad world lines is not just a curiosity; it's sort of a key ingredient in this, the result of that volume that I was talking about. Okay, I'll stop there.
Thank you very much for the fine talk. Other questions?
So when you introduce kind of this naive space-time metric just by adding on dt squared to the given family of metrics, what you get is incomplete. But it looks to me like if you multiply by some universal power of the scalar curvature, basically something that's positive and that goes asymptotic like at slope 1, that you should get a complete metric. Is that true?
Yeah, so we call this the quasi-parabolic metric. It's probably not a good name, but yeah. So that's a metric on space-time which is complete.
Yeah. What kind of manifolds do you get besides products? I mean,
Well, I mean it's
as space-time. I mean,
it's a good question. I mean, if you think about so right now, I mean conjecturally, I guess in dimension 3, I think people expect that the reality is very similar to what happens for mean convex, mean curvature flow surfaces in R3, which is that while there should be only finitely many singular times, and that at each singular time you should have only one isolated point, which kind of goes singular. Well, that's maybe not quite the right way of saying it, but there should be either an isolated neck pinch, or you could have a situation like what Toby was talking about, analogous to the marriage ring, the wedding ring, right, where the whole manifold goes singular. So if that's true, then the spacetimes which show up here would have a very special structure. Okay? we're very far from knowing that at this point, and the whole discussion is, does not assume anything like that. It allows you, maybe one can use this framework to try to approach a statement like that.
But besides products, which examples you can build, actually?
Well, I mean, okay, so the neck hinge would be a good example, right? So you have something, it goes singular and going forward in time from the singular time. Also, if you look at you have a generic neck hinge, such as the one described by Angan and Knopf. So you go backward in time toward the singular time, then, so the singular time slice is non-compact with two ends, right? And then you have this modification, which so then it becomes compact in earlier time slices. And it seems that this language using the Ricci flow spacetime is the intrinsic way of describing that process.
Okay.
But I mean,
What is that? Your plans or they don't appear in the
no, they do appear in the limit in some sense. Yeah, they do appear in the limit, right? Because so which limit are you referring to?
So if you start with the flow of the surgery, you go to the limit. So do you really see so this back point?
Yeah. So I mean, if you think about this generic neck hinge,
Yeah.
right? So go past the singular time, right? So now you see two compact manifolds with these kind of fingers, right? And as you now run time backward toward the singular time, then the curvature in these regions here is going to blow up, right? And what I'm saying is in each of these regions there will be exactly one point. I mean, it's not in the statement, but it's actually in the proof. That there's exactly one point in each of those regions which goes singular.
So you don't take these points out of the slices. So do you really stay in the...
Right. I mean, you could remove them, but then you're going to destroy other properties of the space-time. I mean, in some sense, this is the maximal object that you can talk about with still good geometric and analytic properties.
Okay. There's a question, so let's say speak again.